Hi, in this video we are going to look at balancing a chemical equation using the inspection method. Okay, so say for example you have an equation like this. So let's use a very simple equation first. So you have hydrogen gas and oxygen gas reacting to form water. Okay, so again notice that this doesn't follow the law of conservation of mass, because if you count the number of elements on the reactant side and on the product side, they are not equal. So for example, here you have 2 times 1, so there are 2 hydrogen atoms, and there are 2 oxygen atoms. But on the other side, you have 2 hydrogen atoms, but you only have 1 oxygen atom. And again, the key here is, in science, nothing really goes away, or nothing is created, and nothing is really destroyed without any reason. So if you started with 2 hydrogen atoms, you should have 2 hydrogen atoms on the product side. So here you have 2 oxygen atoms on the reactant side, but now you have only 1 oxygen atom on the product side. So this is not good. It's as if 1 atom was suddenly lost in the equation, and that's not acceptable because we have conservation laws. If you started with this amount of atoms when you started the reaction, you should end up with the same amount of atoms, because remember, a chemical reaction is only a rearrangement. So if you are rearranging atoms, you are not creating any more atoms, you are not removing any atoms. So the number of atoms must be the same. Now obviously here, in order to balance this, you have to kind of put a coefficient here. Put a coefficient here 2, and you can put a coefficient here 2. That way, the equation is now balanced. You have now 2 times 2, you have 4 atoms, and you have 2 times 1, you have 2 atoms. And then for here, you have 2 times 2, that's 4, and then 1 times 2, that is 2. So you now have a balanced equation. Okay, so just remember, in balancing an equation, you cannot change the coefficient. I mean the subscript. You can only change the coefficient, because remember, if you have, for example, O2 versus O3, meaning you're changing the coefficient. This means oxygen gas. Well, this means ozone, the chemical that makes up the ozone layer. So if you change the coefficient, you are changing the composition of the substance that is involved. So that's not good. The equation is meant to be like that. We already know that it's hydrogen gas and oxygen gas that's involved, and what will be formed is water. So if you change O2 to O3 just to balance things up, that's not good, because now you're using ozone instead of oxygen gas. So again, you don't change the subscript. You can only change the coefficient. And why can you change the coefficient? Because if you have, for example, O2, which is understood to have a coefficient of 1, versus 2O2, which is having a coefficient of 2, this simply means you have an oxygen gas, meaning an oxygen bonded to itself. So there are 2 oxygens bonded together. This one still means you have oxygen, only that you have 2 of them. Okay, so this is oxygen gas, this is still oxygen gas. The difference is this is 1 molecule of oxygen gas, but this is 2 molecules of oxygen gas. You see, you're not changing the composition. It's still oxygen gas, this is oxygen gas. You're just specifying the number of molecules. Here you have 1 molecule of oxygen gas, here you have 2 molecules of oxygen gas. So this is the reason why you can change the coefficient, but you can never change the subscript. Okay, so that's the idea. So how do we balance an equation using the inspection method? Well, first you count the number of elements on each side. So obviously you only have hydrogen and oxygen here. So again, this is 2 times 1, so that's 2. 2 times 1, that's 2. 2 times 1, that's 2. 1 times 2, that's 1. And then, very simply, inspect. That's why it's called inspection method. Inspect which elements are not balanced. You have 2 hydrogen, you have 2 hydrogen atoms, you have 2 oxygen atoms, and then suddenly you have 1 oxygen atom. So what does that mean? That means this is not balanced. This is not the same. So again, how do you increase this number so that this becomes 2, that becomes 2? Again, change the coefficient. Instead of the coefficient here, which is understood to be 1, make it 2. That way, you now have 1 times 2. This now becomes 2. So you update the count of the what we call a counting table, and now the oxygen is the same. But as you notice, because this coefficient also applies to the whole molecule, the hydrogen atom is also affected. So now we have 2 times 2, so this now becomes 4. So after you update the one of the elements, also update the other elements that are affected by the change of the coefficient. So now it's like, okay, you now balance the oxygen, but you have unbalanced the hydrogen. So no problem. You have 4, 2. You can increase this number to make it 4. So again, how do you do that? You use a coefficient here that makes this 4. So you use 2. Okay? So now, all of a sudden, you have the equal number of atoms on the reactant side and on the product side. So again, this is done just by inspection. You're just looking at it, and normally the normal way is to adjust the number with a smaller count. So you notice we have 2 versus 1, we adjust the 1 to make it 2. And then we had 4 versus 2, we adjust the 2 to make it 4. So that's one way that you can do it. You can inspect the count of elements and then look for the element with the lowest number, with a smaller count, and then adjust the smaller count. Okay, that's one. But again, there are many ways to kill a cat. So there are many ways to do inspection method. So another way is this. So you have 2 times 1 is 2, 2 times 1, that's 2. This is 2 times 1, so that's 2. And this is 1 times 2, so that is 1, right? And you say, okay, sir, a while back, I have 2 versus 2 and 2 versus 1, and I adjusted the smaller molecule. I mean the smaller number. But what if I want to adjust the bigger number? That's also okay. You can adjust the bigger number, but how do you make this 2 be equivalent to 1? You change the coefficient. How? Multiply it by 1/2. You see, 1/2 times 2 is 1. So now, all of a sudden, this is balanced. You have 2 hydrogen atoms, 2 hydrogen atoms, 1 oxygen atom, 1 oxygen atom. Okay? So this is now considered balanced. The problem is, when writing a chemical equation, there is a convention. And the convention is, we use the coefficients here that are in whole numbers. Okay? Because, think about it, it doesn't make sense to have 1/2 of an oxygen molecule. Right? It doesn't make sense to have 1/2 of an oxygen molecule. So what we do is we multiply the whole equation by a number that would make this a whole number. And that would be 2. Okay? So I'm multiplying this not just on the left side, but both sides. Remember, in an equation, let's say, for example, you have 5 equals 3 plus 2. If you multiply the right side with 3, that's okay, as long as you also multiply the left side with 3. So this becomes 3 times 5 is 15. This is 3 times 3 is 9. 3 times 2 is 6. And you see, the equation remains valid. As long as if you multiply 3 to the right side, you also multiply that to the left side. Obviously, it distributes like that. So you still have a valid equation. So this is what we are doing. We are multiplying 2 to all, so that this would be whole number. So what that means is this will now become 2. And 2 times 1/2, this now becomes 1. 2 times 1, that becomes 2. So now you have a balanced equation, because if you update the number, the counting table, you have 2 times 2, that's 4, and then 2 times 1, that's 2, 2 times 2, that's 4, 1 times 2, that's 2. So you now have the balanced equation. So notice that we ended up with the same answer that we had in the first method. What was the first method? First method was we adjust the count of the element that is the smaller one. The smaller count, we adjust it to match it with a bigger count. But in the second method, we adjust the bigger count to make it smaller and match it, be it equal to the smaller count of the other side of the equation, right? But is there a preferred method? No, there's none. It depends on the situation. It depends on the situation. Sometimes it's faster to, or most of the time it's faster to adjust the smaller count. But there are some cases where it's actually faster if you adjust the bigger count and make it smaller. So it's up to you. So it's really inspection. So this entails some trial and error because remember, you have to kind of adjust the coefficient and then adjust the count and then adjust another coefficient and then adjust the count until everything checks out. So for example, let's have something that is quite more challenging. So let's say C8, which is octane, H18 plus oxygen gas, and this forms water and carbon dioxide. Right, so what we can do is we can again count CHO. On the other side also CHO. C is C 8 times 1, that's 8. 18 times 1, that's 18. 2 times 1, that's 2. And this is 1 times 1, that's 1. H is, H is 2 times 1, that's 2. C is 1 times 1, that's 1. But here you have to be careful with the oxygen because oxygen is found in two terms. So here you have 1 times 1, which is 1, but there's another term, so you have to add that, plus 2 times 1, so that's 2. Okay? And obviously that is equivalent to 3, right? So now you have 8 versus 1, 18 versus 2, 2 versus 3, right? So it's not balanced. So again, you use the first method. The first method is we adjust the smaller count. So the smaller count is this one. So 1 versus 8, this is the smaller count, 1. So we can change this such that it will match with here. So obviously you have to use the coefficient 8 so that this becomes 8. But again, that coefficient also applies to the oxygen here. So now you have 8 times 2. So this would be 16. So this second number would be 16. Right? And this one is still 1 because the coefficient here did not change. But 16 plus 1, that's 17. So now you got the carbon checked. You got the carbon balanced. Now you have to worry about the hydrogen. So again, 18 versus 2, you can adjust the smaller 1. So you adjust this to that it becomes 18. So I have to have 9 here. So that you have 9 times 2 is 18. And again, don't forget that that coefficient does not just affect the hydrogen, but also affect the number of oxygen. So 1 times 9. So this is the first count of the oxygen, 1 times 9. So this 1 here becomes 9. So you now have 9 plus 16. This becomes 25. So now you've checked the number of carbon, right? So that's 8 times 8 equals 8, 18 equals 18, and then you have 2 equals 25. So now here, this is the discrepancy. So you have 2 versus 25. Now, how do you do this? How do you match 2 versus 25? So again, you can say that, well, what do I multiply to this so that it becomes 25? Okay, so obviously the answer here is 12.5 because 12.5 times 2 is 25, right? So what happens here is this becomes 25. So now you have a balanced equation. 8 is to 8, 18 is to 18, 25 is to 25. Okay, but again, writing a balanced chemical equation has a convention, and the convention is it must be in whole numbers. So it must be 1 whole number, whole number, whole number, whole number. In this case, it's not whole number. This is 12.5, right? So you have to multiply it with something that would make it whole number. So again, I'll multiply everything by 2. So if I multiply everything by 2, this becomes 2. 12.5 becomes 25. 9 becomes 18. And 18 becomes 16. And 8 becomes 16. And once I do that, that's now in whole numbers. We will update the count also. So now we have 2 times 8, 8 times 2. So this is 16. And the carbon on the other side, that's 1 times 16. So that's 16. So it's still balanced. How about the hydrogen? 18 times 2. So that gives you 36. And here you have 2 times 18. So that gives you 36. So it's balanced. Then how about the oxygen? That's 2 times 25. So this is 50. How about the oxygen on the other side? Well, that's 1 times 18. So this is 18 plus 2 2 times 16, that's 32. And therefore, 18 plus 32 is 50. So now you have balance. 16 is to 16, 36 is to 36, 50 is to 50. And you're following the rules of writing a balance equation, which is it's in the lowest form whole numbers. Because this is 2 is to 25 is to 18 is to 16. Okay? So that's the idea for the inspection method. So not only will you inspect, adjust the coefficient and inspect and adjust the coefficient, update the accounting table, and inspect if everything is balanced, and then adjust another coefficient, and then, you know, update the table and then balance. But you have to make sure that the final coefficients are in whole numbers and in the lowest terms. So, for example, here I could write 4 is to 50 is to 36 is to 32, right? But that's not in the lowest form. The lowest form is 2 is to 25 is to 18 is to 16. So that is the inspection method. Basically, you're inspecting the count of the elements in the reactant versus the product side. And then you are adjusting coefficient, updating the table, and then inspecting again if it's balanced. If it's not, you again do the same, adjust. Sometimes, most of the times, you have to adjust the smaller count to match it with a bigger count. But sometimes it's actually easier to adjust the bigger count and make it smaller so that it's faster. Okay, so that's the inspection method. Now there are some tips for the inspection method. Inspection method, one of the tips is look for the elements and try to spot them. So for example here, in our example, like the last one, which is C8 H18 plus O2, and then CO2 plus H2. Notice that hydrogen appears once on the reactant side and once in the product side. Carbon appears one in the reactant side and one is in the product side. But notice that oxygen appears once in the reactant side but twice in the product side. What does that mean? It means that oxygen is troublesome, meaning it's difficult to adjust the oxygen. Why? Because, for example, you're adjusting the number. You don't know if you should adjust it here. You should adjust the coefficient of the second location, or you should adjust the coefficient of the first location. So in that case, if this is the case, always adjust the elements that are found in multiple places. So in this case, oxygen is found in multiple places. So it would be suggested that you adjust first the carbon, you adjust first the hydrogen, because both of them appears only once on the reactant side and once on the product side, once on the reactant side and once on the product side. And then always put it in the last priority, atoms that are found in multiple places, because that would be very difficult to do. Okay, so to give you an example, just to give you a sense of what I'm talking about. So for example here, CHO here. So now you have 1. So oxygen is 2 times 1, that's 2, plus 1 times 1, that's 1. So now you say, okay, how do I adjust, how do I adjust this one? And then this is 2 times 1 is 2, right? So now, for example, how do I adjust this one? I need this to be 2. So where do I adjust? Do I adjust here? Do I adjust here? Do I adjust here? So now you have to think about it, because there are multiple places that you can do that. Unlike the carbon, for example, carbon, you have 8 and 2, 8 and 1 here. So now it's very easy. You only have to adjust either this side or that side. And again, in this case, it's easier to adjust the smaller number to match it to the bigger number. So you don't have to think. But in oxygen, again, do I adjust here? Do I adjust here? Do I adjust here? Because they are found in multiple places. So put them in the last priority, elements that are found in multiple places in an equation. Okay. Now, in some cases, it's even impossible to kind of solve using the inspection method. just because the equation is very, very difficult to begin with. Okay, it's very, very difficult to begin with. So for example, if you have, for example, this one, so you have K potassium permanganate reacting with sulfuric acid, uh, forming potassium sulfate plus MnSO4 plus water plus oxygen gas. So this is horrible because look at the oxygen. Oxygen is found in 2 places in the reactant side, and it's found in 3 places, 4 places in the product side. So in this case, I would suggest you would solve for the equations for the elements that are found in single places. For example, uh, potassium is found only in here and in here, once in the reactant side, once in the product side. Manganese is one in one place in the reactant side, one place in the product side. Hydrogen is found in one place in the reactant side, one place in the product side. Sulfur is in one. Sulfur is now in 2 places. Look at that. It's in 3 places. Once in the reactant side and twice in the product side. So that's troublesome. That's troublesome. Oxygen is found in 6 places, 2 in the reactant sides and 4 in the product side. So in these cases, when you find things like this, it's an indication that you might be able to solve them using the inspection method, but it would be very difficult. And if you have a chance of solving it using the inspection method, try to solve first potassium because it's found once in the reactant side, once in the product side. Magnesium, oh sorry, manganese, once in the product side, once in the reactant side. Hydrogen, which is once in the product side, once in the reactant side. And then solve last the sulfur because it's found in one in the product side, reactant side, and 2 in the product side. And oxygen because it's found in 2 places in the reactant side and 4 places in the product side. And I believe that if it's only one element that's found in multiple places, it's still solvable using the inspection method. But once you have 2 or more, it becomes to be very, very difficult. And for that, we have the second method of balancing the equation, which is what we call the algebraic method of balancing a chemical equation. And that algebraic method will be the topic of the next video after this.